Welcome to the third day of the RP 2020. Today I have the privilege and pleasure of introducing to you the first plenary speaker of today, Alan Winfield, who is Professor of Robotics at the University of the West of England, visiting professor at the University of York, and Associate Fellow at the Leverhulme Center for the Future of Intelligence and University of Cambridge. Professor Winfield's main research is in cognitive robotics, but more recently also in machine ethics and HRI, investigating conditions for human trust towards robots. At the same time, he's highly active in engaging the public on ethical issues arising with robotics and actively works for changing robotics education and industry. He's one of the central drivers in the Global Standards Association of Engineers, the IEEE, promoting the introduction of new standards of transparency. We are particularly pleased to have Professor Winfield with us today, bridging over into the field of robophilosophy from the side of engineering, and are looking forward to his discussion of robots who know themselves, at least enough to explain themselves. So thank you very much for being here with us today. And before I give the word to Professor Winfield, just again, a reminder of the practical format. You're more than welcome to use the chat functionality to interact with each other. Please make sure to also include all attendees when you chat so that everybody can read along. After Professor Winfield has finished his presentation, I will draw literally a line in the chat where you can then put in the questions you want us to take up with Professor Winfield. So that said, Professor Winfield, welcome, and please go ahead, enlighten us.
Hi, morning Marco, morning everyone. Can you hear me okay?
Yes, perfectly.
Great, okay, and I just wanted to introduce my dog Lola. She knows what's going on. I think that's kind of important. Otherwise, she might start barking during the presentation. But yeah, and I'll put you down now. Thank you. So thank you so much for the invitation. I've hugely enjoyed the conference so far, and such a shame not to be with you. Of course, I think I was last. I've been once before to Robophilosophy. I think that was probably 4 years ago, and hugely enjoyed my visit then to Aarhus. So let me share my screen and open my presentation for you. I hope that this is visible to everybody. So as Marco said, yes, I'm an engineer, so I'm afraid you won't get very much philosophy in this talk, but I hope you might find it interesting, and I'm looking forward to your questions and comments afterwards. So I'm going to be essentially bringing together a number of different themes, which in fact I've not brought together in a talk previously. So this is really a new talk. The talk is in 3 parts. Firstly, I want to reflect on the importance of transparency and explainability for social robots. Then I'm going to describe in the second part of the talk my work over the past, I would say, 6 or 7 years in what I call artificial theory of mind. And I'll show you some experiments, some experimental work with real robots in that section. And then in the final part 3 of the talk, I'm going to introduce a new project that we have called RoboTips, a project which is really majoring on responsible robotics. And in that part of the talk, I'm going to introduce the ethical black box and finish really by drawing all of this together with a candidate, if you like, architecture for robots that can explain themselves. Okay, so let me dive into part one on transparency and explainability. Now, it's very interesting, I find, and actually quite heartening, because I've been a champion of transparency for some years, that in the very interesting survey paper in Machine Intelligence, Anna Jobin and her colleagues in last year, 2019, they surveyed no less than 84 sets of ethical frameworks for artificial intelligence. And they looked at which principles appeared most often in those frameworks, and transparency, in fact, comes top of the list. It is the most common, if you like, most popular, and therefore one might assume most important principle, followed, as you can see by this chart, by justice and fairness, non-maleficence, responsibility, and so on. So if you haven't seen that paper, it's well worth checking out. But what do we mean by transparency? Well, many of you probably know that there's a large literature in transparency, and there isn't a lot of agreement over what we mean by transparency in robotics and AI. So what I'm going to describe here are the definitions that we've developed in the standards working group that I chair, the IEEE P7001 working group, which is in which we're writing a standard on transparency. So we consider a system to be transparent if it's possible to discover why it behaves in a certain way, and in particular, why it made a particular decision. And we might want to discover why a robot behaved in a certain way. Well, there are two principal reasons. Actually, there are more than two, but especially if the decision caused an accident, if it caused some harm, or simply because the robot's behavior is puzzling. And really, it's the second one of those that I'm focusing on more in this talk. And again, in P7001, we choose to define explainability as simply transparency for non-experts. So in this Venn diagram here, you can see we have transparency including for experts, and then explainability as a subset of that for non-experts. In other words, transparency that can be expressed in plain language. Now, actually, many experts will need transparency expressed in plain language, for instance, lawyers or expert witnesses, for instance. But nevertheless, I'm particularly interested in this talk this morning on explainability. Now, transparency, and I'm sure that you'll appreciate this if you haven't thought about it already, transparency does not come for free. You cannot and must not assume that systems are transparent without some work to make them so. They are essentially properties of systems, engineered systems, AIs, robots, and social robots in particular, that those systems might have more or less of. They're not intrinsic, they have to be designed for, they have to be designed in, and often that might be difficult. So designing for transparency isn't necessarily straightforward. So why I'm emphasizing this, why is transparency so important? Well, the first reason, which I mentioned already, is that social robots can and do go wrong. And I will mention a little bit in part 3 of the talk, the work we're doing on robot accident investigation in the project RoboTips. But secondly, and most importantly for the subject of this talk, social robots need to be understandable by users. And that's really the explainability part of transparency. And thirdly, of course, without transparency, then accountability is impossible. So it's very hard to hold an individual or a group of people responsible for serious failings in a system unless you have transparency. Without transparency, it's very difficult to determine exactly what went wrong and who might be responsible. Now, explainability critically should be built for users, and I think this is really the coming to the as it were, the core proposition of the talk, this talk this morning. And the way I want to express this is very simple. So I think that the elderly lady shown in this image should be able to say to her robot, "Robot, why did you just do that?" and receive a simple natural language explanation of what the robot just did. And then perhaps more interestingly, she ought to be able to ask a different kind of question. "Robot, what would you do if I fall down?" Or, "Robot, what would you do if I forget to take my medicine?" These are perfectly straightforward questions which it's reasonable to expect a robot to be able to respond to, again, in natural language. Now, how would we build the facility, that kind of natural language, intuitive explainability into robots? Well, essentially, that is the subject of this talk. So that's, if you like, the thing that I'm aiming for in the rest of the talk. And just to finish this first part of the lecture, reflecting on what Marco mentioned, I'm part of the IEEE Standards Association Global Initiative on the Ethics of Autonomous and Intelligent Systems. It's a great initiative, so do please join if you haven't already, if you're not already part of it. Very multidisciplinary. I chair this working group, IEEE P7001, on transparency of autonomous systems. In fact, we've been working for more than 3 years now on the standard, and I'm pleased to tell you that about a month ago we finished the first draft, and that has now gone for the first big review stage in the standard development. So it means I'm hoping that the standard will be published in the fairly near future. I don't know when, but I hope it's not going to be too long now. And if you're interested in emerging ethical standards in robotics and AI, then do please check out this paper that I had last year in Nature Electronics. It's just a short comment piece explaining what's going on in ethical standards in robotics and AI. I think you might find it, I hope you might find it interesting. So let me move to part 2 on experiments in artificial theory of mind. And I mentioned this is work that I've been doing for some years, and of course it's great when different threads of your work start to come together. So essentially, I'm summarizing and presenting some of the work that I described in this paper in Frontiers. This was published 2 years ago, June 2018. So what is theory of mind? Well, theory of mind is one of those things that, again, has a different definition depending on who you read. But I think the simplest and perhaps most universal definition is from this classic work by Carruthers and Smith, 1996. The theory of mind is simply the ability to explain and predict the actions both of oneself and of other intelligent agents. And of course, theory of mind, I think, is of fundamental importance to human sociality, human human society. And the working hypothesis, the research question, if you like, of the paper is that simulation-based internal models, and I'm going to explain in a minute what those are, offer a powerful and importantly realizable theory-based, theory-driven basis for artificial theory of mind. Now, I'm not the first person to work on artificial theory of mind, but only one or two of us, there are only a handful of papers that have suggested what I call simulation-based internal models. So let me try and explain a little bit about what those are. But first, I'm going to tell you about theories of theory of mind. Of course, in theory of mind, nothing is straightforward, but essentially there are two theories of theory of mind, which sounds a bit strange. The first one, in fact, is bizarrely called the theory of mind. And theories essentially hold that one agent's understanding of another's mind is based on innate or learned rules. And these are often referred to as simply folk psychology. And the other competing theory is the simulation theory of mind. And in simulation theory, the idea is, if you like, the proposal is that we use our own mental apparatus, in other words, our own model of ourselves, to form predictions and explanations of other people by essentially running our own model for others, in other words, conspecifics, other humans. And it's an attractive, the simulation theory is attractive because I think it permits an experimental approach, which is the one that I followed. Although it's important to say that the implementations that I've built over the past few years integrate some aspects of both theory and simulation theory. So technically, my implementations are hybrids of theory and simulation theory. And I suspect that you know, if we were ever to figure out precisely what the cognitive apparatus in human brains is that gives rise to theory of mind, I suspect that it will turn out to be a hybrid of theory and simulation. So the architecture that I've come up with and implemented with my colleagues, my students and my colleagues in the lab over the past few years is what we call a consequence engine. Now, let me explain a little bit about what this is. And forgive me if this is a very brief explanation of rather a complicated diagram, but if you're interested, you'll find a much fuller explanation in the paper that I just referred to. So I'll start on the right-hand side. So everything from sensory input to the top right and motor commands on the bottom right, that vertical column is a regular robot control system. In other words, a robot accepts sensory input, it samples sensory input, if you like, then a robot controller will, on the basis of that sensory input, determine which action to select. And action selection, I'm sure you're probably aware, is a critically important part of what all robots, in fact, what all animals do. All of us do, I'm doing it right now, we have to select our next possible action. Once that action has been selected, it's carried out, it's realized, typically through motor commands. In other words, outputs to the actuators of the robot. So that is a conventional robot control system. And the architecture that I'm describing here is completely agnostic about what kind of controller this is. because all controllers will have to have action selection. That is simply a fact. So the consequence engine is everything to the left of that conventional robot control architecture. And essentially it consists of this block in the middle, and the most important part of the block are these three components at the top. The robot controller, which in fact is a copy of the real robot's controller, but running in fact in a simulation. So the robot controller, the robot model, which is an internal model of the robot itself, and the world model. So this thing here, the world model, is in fact a model of the world in which the robot finds itself. So these three components are the standard components of any robot simulator. So robot simulators are a very standard technology that we use all the time. What is unusual, in fact highly unusual, is to put a robot simulator inside the very robot that it is a robot simulator of. So, you know, for the psychologists among you, this block here really is the artificial equivalent of an animal and a human's internal model of itself, its representation of itself. And the important thing here is that the world model, in fact, contains models not only of objects in the world, but other agents in the world. So within the world model, we can model other dynamic agents. In other words, other humans, other robots. Now, the world model and the robot model are initialized by this thing called an object tracker localizer, which means that essentially, whenever we run the consequence engine, we first initialize it with the state of the world as it is right now, at this very precise moment. And then what we do is that we loop through all of the robot's next possible actions. And for each of those next possible actions, we run this simulation for some number of simulated seconds into the future. And typically in our experiments, we're running it for about 10 seconds into the future. So then we're looking at what's happened to both the robot and the other agents in the model, and that's the action evaluator. We're saying, okay, what was the outcome of that simulation 10 seconds into the future? So we're doing prediction, if you like. We're predicting what might happen for each of the robot's next possible actions. And for those of you that are familiar with the work of Dan Dennett, Dan, in several of his books, including Darwin's Dangerous Idea, which is a remarkable book, I think, he suggests a conceptual model of animal intelligence with successive layers, which he calls the model of generate and test. What he means by that is the model of how animals, successively more complex animals, generate and test hypotheses for next possible actions. And in fact, this really is an instantiation of Dennett's so-called tower of generate and test. And again, for those of you who are familiar with that, Dennett would describe what I'm doing here as a Popperian creature. So the robots I'm building are Popperian creatures in Dennett's scheme. So you'll see that all of this apparatus on the left runs in parallel with the robot controller. It's obviously computationally intensive, although not so intensive that we can't implement it in real time, which I'll show you in a few moments. But essentially that logic runs through for all of the next possible actions, and we typically run through that cycle twice a second, 2 times a second, and therefore we moderate the real robot's action selection process through this this link here according to the outcomes of the prediction. Now, how we moderate the robot's actions depends on what it is we're trying to do. And I'll now show you several implementations based on different, if you like, aims for this robot's behavior. So again, I apologize if that was a rather breathless explanation of what actually took quite a long time to develop, some years, but there are detailed explanations in the paper and earlier papers that led up to this. So I'm going to start by describing this simple experiment with, in fact, one robot, which is this blue robot here, which contains the simulation-based internal model. And the robot is trying to reach the right-hand end of this rather crowded corridor, which is full of these red robots, which are not intelligent robots. The red robots do not have a simulation-based internal model. They're just running simple obstacle avoidance controllers. So they're bouncing around the corridor like a bit like billiard balls, if you like. And the blue robot is trying to get to the end of the corridor while maintaining a safe, if you like, distance between it and any of these red robots. It's a bit like you trying to run down an airport corridor, not that any of us have done that much recently, of course, when seemingly everybody else is coming in the opposite direction. And you're doing it trying to not crash into anybody and maintain a safe distance. And just to show you those small lines that are protruding in front of both the blue robot and the red robots are the predicted path of those individual robots, if nothing else happens, if you like. Let me show you that with real robots. So this arena, which in fact is actually an old football arena, we're not using it for football, robot soccer, but here we have the intelligent robot on the left, which has to move towards the right-hand side. It has the simulation-based internal model I've just shown you, and these other robots are moving from essentially the right to the left. So, and this work is discovered, is rather detailed in this paper, also 2018. The experimental work was done by Christian Blum, and here is a movie. I hope it works, and I hope you can see it okay. Again, keep your eye on this robot on the left. That's the one with the simulation-based internal model, and it has a reasonably comfortable journey through the corridor until about now, and then it starts to have to take evasive maneuvers. Now, just to give you an idea of the simulation budget, this robot is running the simulation-based internal model. It's cycling through it 2 times a second. And for each of those, in each of those half-second cycles, it's modeling around 30 next possible actions. And for each of those, it's simulating 10 seconds into the future. So that means that in every second of real time, the robot is actually simulating and predicting about 600 seconds of simulated time into the future. So this really just shows you that we can, in fact, run these simulation-based internal models in real time. And this movie was not speeded up. That was in real time. So it works very nicely. Now, we also ran, I think, a really interesting experiment. I got one of my students to try this out. I wanted to run an experiment where you have 2 robots, each heading in the opposite direction. The one on the left and the one on the right is each heading to the opposite end of the corridor. And I wanted to see if those robots would would do the kind of dance that humans often do. You know, if you're walking along the pavement and someone is walking exactly in the opposite direction and about to bump into you, then sometimes, not always, you will step to your right and they will step to their left, which means that you're still about to bump into each other, and then you'll engage in a kind of dance. I'm sure you've all experienced this. And I wanted to test the proposition of whether the same thing would happen with robots, where each robot has a simulation-based internal model of itself and the other robot. And I think this is probably the first, possibly the first experiment ever with robots that each have a simple theory of mind for another agent. And what I have here are simple GIF representations of the two. Oh, I'm sorry, that went on. So the one on the left, bottom left, is robots that pass each other perfectly nicely, and that typically happens once every 4 or 5 times, about twice every 10 runs. Whereas on the right, the robots didn't pass each other nicely and engage in this kind of dance. And you can see the outcome of that, the trajectory of the two robots above that. And again, it's interesting that these little whiskers that are coming out of the robots show all of the next possible actions that are being tested in each of the cycles of the simulation-based internal model. So again, I think that's a really interesting demonstration of that. I should explain also that we ran these experiments both with real robots and in simulation. The beauty of running them in simulation is that you can actually see what's going on, as it were, in the quote mind. I mean, the robots don't have minds, but nevertheless, within the simulation-based internal model. So we can actually see what's going on step by step with these beautiful GIFs that you know, my students produced. So again, I think an interesting experiment, simple experiment with artificial theory of mind. The third experiment I want to show you is really an early work on building minimally ethical robots. I've done some work on machine ethics. I'm not sure that ethical robots are a good idea. So, but again, you know, that would be the subject of another talk. So, you know, that would be a talk about the ethics of machine ethics. But I'm not going to get into that now. Instead, I just want to show you the experimental results because they're interesting. I hope you'll find them interesting. So the top experiment, the first experiment we did with these, again, with these epoch robots, we have the A robot, which is called A robot because it implements a simple form of Asimovian ethics. In fact, it implements actually Asimov's first law of robotics. And the robot, the A robot, is trying to, it has a goal of its own, which is to reach this point over here on the top right, nothing to do with the goal as in football, but just a destination, which means the A robot has to avoid falling in this hole in the ground. The H robot is, again, an unintelligent robot pretending to be a human. It's a hapless human heading towards the hole in the ground. Perhaps the human is you know, on their mobile phone, not paying attention to where they're going. And the A robot implements Asimov's first law of robotics, so that the experiment is to see if the A robot will, in fact, will put itself in harm's way to prevent the H robot from falling into the hole, and also avoid itself falling into the hole. We also did the same experiment with these now robots. My colleague Dieter van der Elst which I'll also show you, really, which was, if anything, an attempt to show that the idea of a simulation-based internal model is transferable to very different robots, these humanoid now robots in this case, and much more complicated robots, I have to say. So the ethical robot experiment started with a thought experiment back in about 2013, something like that, 7 years ago. And the thought experiment was very simple. Imagine that a robot has 4 next possible actions. Here is a human heading towards a hole in the ground. If it chooses actions A, which is stand still, B, which is turn left, or C, which is straight ahead, in A or B, the robot is perfectly safe, of course, but the human may well come to harm. If it chooses action C, then both the robot and the human will fall in the hole. If the robot, on the other hand, chooses to turn right, then it might collide with the human, which is less serious than the human falling into the hole. And we express this as an ethical rule, and this is built into the consequence engine, which is this. If for all robot actions, the human is equally safe, then output the safe robot actions, else output the robot action which results in the least unsafe human outcome. And again, if you're interested in how we figure out which is the least unsafe human outcome, then check the papers. But essentially, this is the rule which is applied for each of the outcomes of running the consequence engine, running the internal simulation-based internal model for each of the robot's next possible actions, bearing in mind that that model is also determining the outcomes for the other agent in the world, which in this case is a human. So here is our trial 2. We did trial 1 with no human as a baseline, but I won't show you that. So trial 2 has the A robot on the right, the human, and you could see then that the A robot diverted from its path, headed off the human, the H robot, and then went to its destination position over here. So it works very nicely. The same simulation budget that I mentioned for the corridor experiment, and you can see speeded up. So really the experiment, the proposition works very well, at least for this ultra simple context. Clearly, the robot is only, even if it's, I mean, I would argue it's reasoning about ethics, but only in a very minimal context. So it is at best minimally ethical and implements a trivial form of consequentialist ethics. Now, I'll show you in a moment or two an experiment, because once we drafted the paper, I said to Christian and Wengu, I said, look, this is a bit boring because it seems to work. Why don't we add a second human to make it more interesting? And I'll show you that in a minute. But first, I'll show you the trial with 2 now robots. Here, the red robot is the human. The blue robot is the Asimovian ethical robot, and the tower on the right is danger, and this is the destination. The tower on the left is the destination for the ethical robot, and you can see that it works just fine. And this was published more recently in Cognitive Systems Research, and essentially an architecture inspired by the simulation theory of cognition, which I didn't mention. So simulation appears in both theory of mind and theories of cognition, which you can see why that's attractive to me, because it's something that you can build. But here is, I think, a demonstration of I suspect, we believe the first ever real physical robot facing a balanced ethical dilemma. And oh dear, the ethical robot has completely failed to save either of the humans H1 and H2. Both fall into the hole. And you'll see as this speeds up that there the ethical robot did save one of them, but often it doesn't save either. And you can see there's some randomness because sometimes the H robots don't head into the hole anyway. They're heading off in random directions each time, but in broadly the direction of the hole. So this was a puzzle to us until we realized, of course, that the reason that the A robot is failing to even save one of them reliably, in fact, it saves one of them a little less than half the time, is very simple. It's because the A robot is essentially cycling through the consequence engine, as I mentioned before, at the rate of 2 Hertz. It's running the consequence engine every half a second, which basically means it has an opportunity to change the decision about where it's going next, its next possible action, every half a second. Essentially, it means that the A robot is, if you like, pathologically indecisive. Now, I'm sure you appreciate that when faced with an ethical dilemma, it's not a good idea to be changing your mind all the time. So that's essentially why the A robot failed in this test. So I think it's a particularly interesting failure. And obviously, and often you learn more from failures in robot experiments than you do from the things that worked. So that was the experiments that we've done. And finally, I want to share with you in this part, this second part of the talk, a thought experiment which really leads directly to the proposition that I'm going to come to, that robots could explain themselves. So this is really a paper called "When Robots Tell Each Other Stories: The Emergence of Artificial Fiction." It came out of work I was doing with a narratologist, Richard Walsh, and a computer scientist, Susan Stepney. We had a series of workshops on complexity and narrative. And I realized that a robot with a simulation-based internal model has effectively an imagination. It has an artificial imagination. And in fact, others who've built robots with simulation-based internal models have also called this mechanism a functional imagination. But the idea is that if a robot is thinking, it's not thinking, if a robot is running next possible actions, then essentially it's coming up with a whole lot of actions that never actually get carried out in real life. So what if it narrates one of those what if sequences? What if I turn left? What if I turn right? And then literally speaks it, and a second robot, a listener robot, essentially listens to the narrated what if, if I turned left, I would bump into the wall. And then robot B then plugs that what if sequence into its simulation-based internal model and runs it. Then I posit in this paper, what we have here is an embodied computational model of storytelling. And people have said, well, where's the meaning in the story? Well, I'm just a suggestion. It's an off-the-cuff suggestion. Maybe when you run that heard story in your internal model, maybe that's what understanding is. Maybe that is in fact understanding. So I'll leave that controversial thought with you and move to section 3 of the talk. And I just will take a quick drink of water. Thank you. So I have this wonderful project which started just over a year ago, a collaboration with the University of Oxford and my colleague, Professor Marina Girotka in Oxford. And the project is called Robotips, Responsible Robots for the Digital Economy. Now, it's a 5-year project, which is great. And let me tell you a little bit about what we're doing. The project really grew out of an idea that Marina and I published a paper 3 years ago, 2017, called The Case for an Ethical Black Box. It's a very simple proposition, but I believe a very powerful, and not just powerful, but essential proposition. The proposition is this, that every robot, and in fact, perhaps even some AIs, should be equipped with the robot equivalent of an aircraft flight data recorder. Of course, and here is a flight data recorder from an aircraft. As you probably know, even though they're colloquially called black boxes, they're actually orange, obviously because that makes them easier to find after an accident. But we call our data logger, we call it an ethical black box simply because we think that it would be irresponsible, deeply irresponsible, not to equip robots, especially social robots, with an ethical black box. And that would include robots for children, of course, educational robots, and obviously driverless cars. Now, a major part of the work of the project Robotips is developing the ethical black box, prototyping it. In fact, we're building a reference model which we'll make available completely open source, because we believe that others should implement this and test the ethical black box in different robots and different settings. In fact, we have a number of industrial partners who are working with us on this. But of course, accident investigation is fundamentally a human process of both discovery and reconciliation. And so a major part of the project is actually going to be running 3 different staged, if you like, mock accidents. One in assisted living robots, a second in educational toy robots, a third in driverless cars. And I believe that Robotips is the first project, as far as I'm aware, in the world that is systematically investigating both the technology and the processes of social robot accident investigation. And you'll be interested that for each of these scenarios, we will have 3 sets of human volunteers, the human subjects of the accident, in other words, the people to whom the accident happens. They will, of course, be actors. They'll be in on the scenario. But then we'll also have human witnesses to the accident. They could be naive witnesses, just bystanders like neighbors, or they could be expert witnesses such as a paramedic who arrives on the scene of the accident. And we will also have volunteer members of the accident investigation team. And we're, the idea is that we want to propose not only the technology for accident investigation, but also the process of accident investigation. And the ethical black box is a key part of that. Without data logging, there is really no chance that you can figure out why what happened actually happened. And the ethical black box would typically store compressed sense data, actuator demands, high-level goals, alerts, and decisions, ideally with the reasons for those decisions. Of course, that might be tricky depending on the form of the AI in the robot, or which you can see the blue stuff at the top is our robot control system. And of course, the ethical black box then has standard interfaces to connect and access the EBB data. So we have, we should have conducted our first robot accident already. We haven't, of course, because the lab has been in lockdown since March. But we have, in fact, recently published a paper. You can see it on Archive, essentially describing a fictional accident and, as it happens, a fictional accident investigation. And if you're interested in how we might investigate accidents of social robots, then please check out this paper, this new paper. It's on Archive. It's not yet been published. It's been accepted for a book chapter. So let me then come to the very final few slides of the talk and reflect with you something that I've written about in the past, which is essentially the problem, I think, that needs to be solved with explainability. And it is what I think of as a serious asymmetry of theory of mind. So imagine this situation. An elderly person has an assisted living robot. So we can expect that a reasonably sophisticated near future assisted living robot will have a built-in model of elderly humans, or even possibly a particular human. That's not unreasonable. Now, that may be a simulation model, it might be a theory model. In other words, it might be just a set of rules, preferences, but in a sense, it doesn't matter. The important thing is that the robot has, albeit simple, theory of mind for the human. But will the human? Well, no, the elderly person has no theory of mind for the robot. Actually, it might be worse than that. She might well have completely the wrong theory of mind for the robot, based on preconceptions, perhaps, hype in the press, and so on. So I think not only is there an asymmetry, but it's possible that she has completely the wrong theory of mind for the robot. And that asymmetry means that when the robot behaves in a way that doesn't make sense to her, her confidence in the robot will be impaired, and therefore its effectiveness diminished. I think this is, in fact, in one of the workshops on Tuesday, Anna gave a great talk about why social robots need theory of mind. So, I hope, I'm not sure if Anna's listening, but I hope she might find this interesting. So let me put it all together. Well, this is work that we're doing right now, so I can't show you any results, but essentially, we already have the consequence engine. I described that to you earlier. We know that that works. We know how to build a consequence engine. We are in the process of building our ethical black box. It's conceptually quite simple. It's essentially a data logger. But if you think about the ethical black box for the purposes of explainability, the ethical black box is actually an autobiographical memory. It means that the robot has a log of what it did in the recent past. So I think that answering the question why, in other words, robot, why did you do that, is going to be a relatively, I mean, I don't say straightforward, because in real robotics, in experimental robotics, nothing is straightforward. All of these things take time and considerable effort. But in principle, at least, a simple chatbot shell with a speech input and speech output, where the chatbot shell is simply parsing the the questions being asked of it, robot, why did you do that? The why question is essentially answered by interrogating the ethical black box. Not the purpose for which we proposed the black box, but we think that the black box can be used to extend, and this is in fact part of RoboTips, if you like, an additional aim in RoboTips is explainability, actually not just for users, but also for accident investigators. So, and then of course the what if question is more difficult, but again, conceptually, what it means is essentially using the consequence engine to initialize the consequence engine with the what if. In other words, initialize the simulation with the situation that the elderly person has fallen over or has forgotten to take her medicine, and then literally running the consequence engine so that the robot can predict what it would do in that situation by, in a sense, imagining what it would do. In other words, it's predicting what it will do in that situation. It's not, in other words, the important thing here is that the explainability is not simply a pre-programmed script. What the explanation to robot what if you did, what if is going to be given by the robot actually reasoning on that question, that very question, and narrating therefore what it would do in that situation if it were to actually happen. So I put it to you that is a proposed architecture for robots that can explain themselves. And that brings me to the end. I'd like to, of course, thank my colleagues in the RoboTips team, Marina, Helena, and Katie on the top, and also and the funders, of course, EPSRC, and also my brilliant colleagues and students who did the experimental work in the early part of the talk. So thank you for listening. I'm interested now to take questions. Be very happy to take questions.